Alright, here we go. So I have some good news. Okay? I want you to know that what we have covered in Chapter 6, what we did last class, the calorimetry bit, that, in my personal opinion, is the hard part of Chapter 6. What we're going to learn today will be all new material to you. You did not cover it in Chem 1, but it is not difficult at all. Okay? And the first topic that comes up is something called Hess's Law. And I will put up the definition for you, and then I'm going to give you an analogy to help you understand it. The definition says the change in enthalpy. What does that word mean? Heat energy. The change in enthalpy is the same whether a reaction takes place in one step or a series of steps. Well, before we even talk about what that means, I want you all to be aware that many chemical reactions that you see in the lab, that you see out in nature, that you see in here, whatever, many of those reactions do not occur in just one step, okay? A yields B. Most reactions do not occur in one step. They occur in multiple, what I call mini reactions. Like A forms B, and then B forms C, and then C forms D, which is our ultimate final product. Okay? Most reactions do not occur in one step. They occur in multiple steps. Now, here's your analogy. Okay, we're at Oakton High School, and I want you to imagine that we decide to take a field trip. We're going to take a tour of the White House. Good times. If you were driving from here to the White House, what do you think is probably the most direct route to get to D.C.? 66, yeah. Okay, 66 runs directly into D.C. And let's assume that, you know, it's not rush hour. How long do you think that would take? Maybe 30, somewhere around there. Okay. So you're driving and you've got a person in the passenger seat who's serving as your navigator to give you directions. All right. You take 66, takes you about 30 minutes to get there. Great. Well, somebody else gets in their car with their navigator. They get in the car, and the navigator makes a very serious error in directions and directs you to drive out to Manassas. And then you go from Manassas to Centerville, and then you take a little detour through Loudoun County, and somehow you end up in like Ellicott City, Maryland, and take a little swing by Annapolis, Maryland, and then, okay, now we got it. Now your friend is like, oh wait, I know where we're going. And then you get to the White House. Okay? What an idiot.
Why is he driving?
I don't know. Well, you're driving. He's just the navigator. Shame on you for listening to such ridiculous directions.
Let me drive.
Tell me this. Is the distance between where we began and where you ultimately ended up in these two different people's cars, so these two people, is the distance between where we started and where we ultimately ended different? No, it's not. The distance between where we started and where we ultimately ended up, the distance is the same. Okay? Now, the second car took a much longer route to get to that final place, but they still ended up in the same place. We can use this analogy in terms of enthalpy change for a reaction. Let's say a reaction occurs in one step. That would be like you taking 66, going very directly to your destination. But other reactions take multiple steps to get to that final product. The thing is the enthalpy change between your reactants, original reactants and final products will be the same no matter what path you took to get there. Question?
So, enthalpy is like a displacement?
Yes, it is. Yes, it is. Enthalpy is like a displacement. Okay? And I will show you in just a second what a Hess's Law problem looks like. And for those of you that are very logic-minded and like puzzles and things like that, you're going to love these problems. They are actually kind of fun. It's okay if you don't want to admit it. All right? All right, this is a graphical way to look at Hess's Law. And I'm going to draw something on here. If this graph looks a little confusing to you, let me draw something on here that'll make it look a little bit more familiar. Reactants, products, does that shape look familiar? We've seen these energy curves before. Would this shape indicate endo or exothermic reaction? Endo. It's generally uphill. Products are higher than reactants. That's by definition endo. Okay? But this graph is showing an overall reaction that occurs in 2 steps, or 2 mini reactions. Original reactants to these guys, we'll call them intermediates, and then these guys then turn into my final product. Okay, so this would be a reaction that takes place in 2 steps, and the overall energy difference is 68 kilojoules. But let's say I didn't take this same path. I went over here and la 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 la. Do 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 do. I took a crazy. Oh, I came back over here. But I still end up in the same place. Does it matter that I did all of this? This difference is still 68 kilojoules. Okay? That's what Hess's Law says. It doesn't matter the path you took to get there. From your original reactants to products, the difference is the same. Now, obviously, this is a bit of an exaggeration, but you get the point. Okay? Now, this is a graphical way. This is what a Hess's Law problem looks like. Okay? What's written in white, these are what I call mini reactions. And this slide corresponds, by the way, to the graph on the previous slide. Okay? Here are those 2 steps that it took for my overall reaction to occur. Now, in a Hess's Law problem, you will be adding these mini reactions together. And we've done something similar to this before. If you are going to add reactions together, you can cancel out anything that occurs in identical form on opposite sides of the arrow. Do you see something I can get rid of? Okay, I cannot get rid of O2 because it's on the same side of the arrow. Both on the left. What can I get rid of? Okay, 2NO. Anything else? Nope. When I add everything that's left over, this is my overall reaction. And I also add the heats together to get the overall change. Now, look at this first mini reaction. The fact that delta H is a positive number means what? Endothermic. For those of you that have the slides, if you look at that first step, it was uphill, wasn't it? And then look at the second one. It's negative. That means what? Exothermic. The second step went from the top of the hill down. Okay. And then we add them together to get the overall net difference. Okay. So what a Hess's Law problem is going to look like. You will be given what I call mini reactions. Sometimes 2, 3, 4. I think there's one in your problem set that gives you 5. They also tell you what the final reaction should be. And your job is to manipulate these mini reactions so that when you add them together, you get the proper reaction. Okay? Now when I say manipulate, what do I mean? Well, here's an example. What's happening from this equation in white to this one in yellow? Okay, the products and reactants have flipped. And look what happens to the energy change. Okay, it just changes sign. And guys, that should make sense. If it's, when it's written in this direction, if it's endothermic, which, let's review, does that mean heat is a reactant or a product? Endothermic. Reactant. If you turn the reaction around, heat is now a product, which makes it exothermic. So flipping the reaction is one way you can manipulate it. Here's another way. What have I done from this equation in yellow down here? Multiplied by 3. What happened to the heat value? Also multiplied by 3. Do you remember we talked about enthalpy being an extensive property? What does that mean? It changes when what changes? The amount. Well, I changed the molar amounts, and the heat change will change right along with it. Okay. So we're going to do this example problem together, and then I'll let you do one on your own. Okay. So this is what a Hess's Law problem looks like. I've been given what I call 3 mini reactions, and then I am given the final one, the overall, and they want to know what the enthalpy change is for this overall reaction. Okay? So here's the process we go through. Okay, this is a foolproof way to make sure that you do these problems right. We're going to look at this overall reaction and we're going to take it piece by piece. Here's our first reaction. O gas, not O2, just O. Do you see anywhere up here in these mini reactions, do you see O gas somewhere? Where? Okay, second reaction on the product side. Here it is. Okay? Well, folks, our ultimate reaction here needs O gas to be a reactant. Okay, so you're saying flip it. Alright, I can do that. And if I flip this reaction, this is what I'll get. Let me cross through this. And this becomes negative 495. Now, hold on. Please notice the coefficient. It needs to have a coefficient of 1. And it doesn't right now. Multiply it by 1/2. And what does that do to this number? Also multiplies it by 1/2. So then my reaction, my mini reaction looks like this. Yes, you are. I know that goes against what we usually say. But yes, you can. Okay? So, would you all agree that from my mini equations, O gas is on the correct side and it has the correct coefficient? Are we in agreement? Okay, I'm going to put a check mark over this one. Let's move on to the second one. Do you see H gas somewhere? Okay. Is it on the correct side? Is it the correct number? No. So we're going to have to do the exact same thing we did up here. We'll have to flip it and multiply times 1/2. Okay. Let's move on to the third piece. OH gas. Is it on the correct side? Yes, so I don't have to flip this one. Is it the correct number? No. So that's the only change that I will need to make here. Okay. So ladies and gentlemen, I'm now ready to add these up. Okay, what can I cancel out? Okay. Okay, good. Anything else? Okay. And ladies and gentlemen, is this the reaction I was supposed to end up with? Yes. Okay. Now, that's not what this problem is really asking me to solve for. They gave us the reaction. The reason we went through this process was, first of all, to ensure that we were getting the correct and proper reaction. But really, what they're asking us to solve for is the delta H value. And how do I get that? Add them all up. Okay. Chris, did you have a question? Okay. Now, there are two rules for Hess's Law problems, and I want you to write it down, because it wasn't so much an issue for this one, but it will become an issue when you get to your problem set. Rule number 1. You must use every mini reaction given to you. You must use any mini reaction that is given to you. I don't care if you're given 5, 6, 7 mini reactions, you use every single one. Rule number 2. You may only use each mini equation one time. Now, again, ladies and gentlemen, that was not really a confusing issue with this one, but imagine if we had a final reaction with 3 pieces, but you were given 6 mini reactions. Okay? That must mean that those extra mini reactions are there to simply cancel things out that we don't want in here. Okay? Now there's one other thing I want to say before we go on. Last class somebody asked, does the state of matter matter? Okay? Funny, I know. Yes, it does. Okay, now guys, this is not equilibrium. This is not a situation where we're like going to eliminate solids and liquids. When I say that the state of matter matters, okay, what I mean is, let's say that this H2 was in gaseous form, but this one was in liquid, I could not cancel them out. They must be in identical form. And I believe there's one in your problem set that has water, has H2O in gaseous and liquid form, so you really need to be careful about that. I want you to try this one on your own. Ladies and gentlemen, I want to give you a piece of advice, okay? This particular problem, if you were going through that step-by-step method that I modeled for you, where you take each piece by piece, one thing that's a little confusing in this one is that this second piece of my final equation occurs in multiple places. If that is the case, and you're not sure what to do, skip it. Just skip it and move on to another piece of the final equation that only appears one time. And what you'll end up seeing is that if you wait and come back to this one that's in multiple places, if you come back to it later, it tends to just naturally work itself out, that you'll end up just getting the correct number that you're supposed to because you manipulated for everything else. So again, my advice is if you come across something that appears in multiple of your mini reactions, skip it and move on to something that only appears one time, and usually things work themselves out naturally. Okay. Now, I had you get a textbook for a reason. If you would, please go to the very back of your textbook where the edges of the pages are this sort of purplish color. We're in the appendix. Please go to page A20. Ladies and gentlemen, this huge chart, which actually starts on the previous page on A19 and continues, this chart is your new best friend. Now, do you think I'm going to have you memorize anything out of here? No. Please, have a little faith in your instructor.
Thank you.
Okay? No, there's nothing to memorize here. Alright?
Thank you.
So, when you're going through your problem set, even if the problem doesn't say, please consult appendix blah blah blah, you are expected to know that this is available to you. Now, what if it's a test question? Am I going to let you get up and get a textbook? No. I have to give you information out of this chart. Okay? So if you would, just scan your eyes down this chart. I want you to notice that what's listed here are a whole bunch of elements and compounds. They are basically in alphabetical order. Alphabetical order by name, not symbol. Okay? And you'll notice for each element or compound there are 3 columns: delta H, delta G, and S. You should know delta H. What does delta H mean? Change in heat. Delta G and S are concepts that will come up in chapter 16. We'll get to that later. We're going to focus on this first column. In the heading for that column, do you notice that it says delta H and then there's a little degree symbol? Do you see it? Okay. That degree symbol does not mean degrees Celsius or degrees Fahrenheit. It means these numbers, these heat changes were measured under standard state conditions. Please do not mix that up with STP. What does STP stand for? Standard temperature and pressure. What is standard temperature? 0 degrees Celsius, 273 Kelvin. What's standard pressure? 1 atm. Okay. You can thank the chemistry people for making 2 different conditions have very similar names. Standard state and STP are not the same thing. Standard state means any gas, you may assume the pressure is 1 atm. Now, I want you to notice in this chart that next to every element or compound, you are given the state of matter. Solid, liquid, gas, aqueous. Anything that is a gas, you can assume that these numbers were measured when those gases were at a pressure of 1 atmosphere. For anything that is aqueous, meaning in solution, these numbers were measured when the concentration was 1 molar. You can assume that the temperature, these energy changes were measured when the temperature was not 0 degrees Celsius, but 25. Now where did they get that number, 25? They didn't just pull it out of thin air. 25 degrees Celsius is basically considered to be room temperature. Okay, this room is close to 25 degrees. It's usually a little bit under. Usually our room is like 22, 23. Okay, but 25 is generally considered room temperature. Okay, and do you also notice in the heading of this column, it says delta H, there's a little degree symbol. Do you see that there is a subscript F? Do you see it? Okay. F stands for formation. How do you form something? What does that mean? To combine it, to make it, to create it. Okay? Ladies and gentlemen, these heats that are listed here, they're called enthalpies of formation. That means these are the heat changes associated with synthesizing, making, forming, creating 1 mole of these substances. So let's pick one for example. Let's look at sodium bromide. NaBr. Find it in your chart. Sodium bromide. Remember, they're in alphabetical order by name, not symbol. What's the delta H value? Shout it out. Negative 360. Okay? To form sodium bromide, that means I need to bring sodium, pure sodium metal, and bromine gas or liquid, it doesn't actually matter. If I put those 2 elements together, they make sodium bromide. And what does it mean that the energy change is negative? It's exothermic. So if I had a container where I'm mixing sodium metal and bromine gas, and I put my hands on it, will it feel hot or cold? Hot. Okay? So it's the heat associated with forming 1 mole of whatever's listed. All right, let's look at another one. Find calcium solid. Solid calcium metal. Find it. What's the value? 0. Okay. Find solid nickel. Nickel metal. Find it. 0. Anybody think it's a little odd that these are all 0? How do you form an element? You don't. Okay? They occur in nature. Okay, now we're not talking about the ones that are man-made, that are created in a lab. Okay? You don't create an element. Now, this gets into a little bit of a discussion. If you go over, find carbon. Solid carbon. There's 2 forms of carbon listed there. Graphite, which has a value of 0, and then carbon diamond, which doesn't have a value of 0. It has a value of 2 kilojoules per mole. It's positive. What does that mean? Endothermic. Energy is required to make carbon into a diamond. Okay? Does diamond occur naturally in the earth? Yes. But the forming of changing coal into diamond requires energy be pulled from the earth. Okay? All right. So, all elements, for the most part, are 0. If it's not 0, then I have to give you the number. Okay. Now, it is my personal thought that for you to truly appreciate what's in this chart and to have a thorough understanding, you need to be able to write what is called an equation of formation. And that's not difficult, guys. Find NO2 gas in your chart. Find it. Shout out the number. 34. Okay? 34 kilojoules. It's positive. 34 kilojoules are required to put nitrogen and oxygen gas together in order to form 1 mole of that compound. Now, why are there 2's right here? Because these are diatomic elements. And if any of you are wondering why there is a 1/2 there, when I've said so many times we don't do fractions in chemistry, the definition of energy of formation is forming 1 mole of the substance. This coefficient must be a 1, and you back solve for your coefficients of your reactants. So, let's just do a little quick example here. Okay, this is a compound called methanol. How do you write the element carbon by itself? C. Plus, how do you write hydrogen by itself? H2. How do you write oxygen by itself? O2. Yields, and then I'll write the formula. And this must have a coefficient of 1. So how do I fix these coefficients back here? A 2 and a 1/2. Okay? That is the equation for the formation of 1 mole of methanol. Okay? Now, what are we going to use these numbers for? Well, I'll show you. And guys, this is so easy. A 6th grader could do this. Okay? Are you ready? You are smarter than a 6th grader. Now, I'm not going to lie. This looks very ugly. That looks horrible. Okay? This is very typical of math people. They take a very simple concept and make it look like another language. Okay? let me break this down for you. This is so simple. Okay? What do you think RXN means? Reaction. It's the chemist's way of shortening the word reaction. Okay? The heat change. Listen. The heat change associated with a reaction equals. What does sigma mean in math? The sum of. Little n means moles, or more specifically, coefficients. And where's this? Heats of formation? In the chart. Basically what this is saying is the heat of your products from the chart minus the heat of your reactants from the chart. No. Let me show you. Okay, we're going to do this first bullet. We're going to do this one together. This is so simple. Let me change this, give myself a little more room. Okay, the heat of the reaction equals, big bracket, products come first. Please find in your chart CO2 gas. Find it. Negative what? Okay, negative 393.5. Now there's a coefficient of a 2 in front of it. 2 times negative 393.5. Plus, I have another product. Find H2O gas. Tell me the value. Negative 242. It has a coefficient of 3. Close bracket. That's the heats of my products minus. Now it's time to look at reactants. Find this guy. It's called ethanol. Find it. Tell me the value. Negative 278, and it has a coefficient of a 1. O2 gas. 0. You shouldn't be looking for it. 0. Put it in your calculator, and this is what will come out. Okay? What would the units be? Where are you getting that? Okay, the chart, all of the numbers we got out of the chart are in kilojoules per mole, and when we were multiplying times the coefficient, we were basically just multiplying times moles. So, it's just kilojoules. So easy. You do the second one. Isn't this so easy?
Yes. No,
So easy. Okay, I'm just going to tweak it just a little bit. Actually, before I change the slide,
This is the court usually, and she's like, this is a Chem 1 problem, and then she goes, it sounds like so much
no, that's not a Chem 1 problem. This is safety.
That's usually what happens. I just like die inside. Just get Chem 1.
Ladies and gentlemen, I want to make sure that you recognize the difference between these two variables. Both of them are a change in heat. Okay? when you see this little subscript F, and what does F stand for? Formation. Fun, of course. Where does your brain need to go? Chart. I want you to think chart when you see that. This, listen, this one is products minus reactants. This is the one that gets plugged into products minus reactants. So, if you look at this one, and you look at the thing that I'm asking you to calculate, it's a heat of formation. What do you think when you see formation? Chart. Okay, great. Go look it up. It's not there. Ha-ha! Okay. Gotcha! Okay. So, it's not there. You're going to have to figure it out. Well, first of all, guys, what I am giving you here, if you see delta H and there's no subscript, that is the same thing as this one, the heat of the reaction. Figure it out. How come the units for my final answer are kilojoules per mole and not just kilojoules? Heats of formation are in kilojoules per mole. Heats of reaction are in just kilojoules. And guys, how come my little, what's inside the products here is so short? There's 3 of them. 2 of them are pure elements. So their value is 0.